All right, so let's move on in part 4 here to filters. And we will begin with passive filters. So again, we're dealing with frequency response of the circuits. And filters, like it says, are designed to exclude frequencies, or that's pretty much all we can do. And we'll combine them in different ways to do that. So we can make filters of several types. I mean, when you think of the basic question is a frequency present or not? So we have yes and no, and how are the ways we can combine that? Well, the first would be we could do a low-pass filter, which says, just as the picture shows, there's a pass band, some cutoff frequency, and a stop band. And what we'd really like, if we can have it here, is this. These corners. We would like those corners to be really sharp. Everything below the frequency is on, everything above the frequency is off. So the whole trick of filter design is going to come down to how well we can manage the corners. The next type would be to reverse the situation. Pass the high frequencies, stop the low frequencies, and again the corner. Right now there's some other possibilities here. A natural one would be, well, I've got a whole range of frequencies right here. Whoa, a long range of frequencies. And I want to pass some in the middle. Okay, and as time goes on and you encounter various applications, it'll be pretty obvious. The high pass, the low pass, I mean, this is like hearing aids and such. Fancier types of hearing devices or frequency measurements. You like to be able to limit the response. And once again, in order for that to be really good, it's the ability in our circuits to make these corners that's going to matter a whole lot. The inverse of this, of course, is the band stop, where you pass everything except for some frequencies, out here in the middle. You like to stop all these. Okay, you could imagine we could cascade all sorts of possibilities, and we might have some multiplexing thing going on where you can stop and start and stop and start and stop and start. And theoretically, possibly, if we wanted to go through the effort, we could do this. This is not something we're going to study. That's kind of like a little silly. So let's start. We're going to look at the 4 types I showed. The low-pass filter. And we'll do these as passive filters first. So we're back looking at our RC circuits, RLs, RLCs. That's what we're doing here. So here we are. You have done this circuit already, right? When this thing, instead of a function of time, was just a DC source. You've done this as a DC circuit, right? And this has a time response depending, if you do it, plot this as a function of time, right? The voltage across the capacitor can charge up like that. So you're familiar with that. We're not driving it now with a DC source, but nevertheless, we're still able to analyze this and think of it as something that has an active component, not just, something here in this capacitor is going to affect, and this capacitor is going to affect how things go. So let's make the transfer function now. And even though this shows time, so it's not DC, but it's time variant, okay? But now we're looking at the frequency response, and that's what we're going at. That's what we've been going at in this whole chapter, and we're going to stay at that now. I just want to reemphasize the circuit is really very simple. This is just a voltage divider, right? What's the voltage across the capacitor with respect to the voltage across the whole thing, right? And so you're just dividing the voltage action between the resistor and the capacitor. And that's all we've done here, right? Here is the impedance of the capacitor. This is equal to Z sub C over Z sub R plus Z sub C. All right, there's no real fanciness here that says, oh, now we're not doing simple divider networks or current dividers or voltage dividers. All of that stuff is still present, and you need to keep thinking about it that way. All right, so if I factor this out, and I guess if I, let's see, if I took and brought up an eraser here, I probably need to erase a little bit of my stuff here. Okay, and we'll get back to the pen. But so here is that transfer function now cleaned up a little. How did I clean it up? I just multiplied by j omega c, and that turned this into a 1, and this into a 1, and this into a j omega rc, right? So now we have standard form, something we like because we know this indicates where things like breakpoints are. Just look at this, and you mathematically can see the low-pass filter. What happens at low frequencies? This term is when omega is low, right? This term approaches 0 or is 0. So you got 1. And all of that continues until you hit omega equals 1 over RC, right? The so-called break frequency. So here is the magnitude going on, and all I've done is the math, which is simply finds the magnitude of this vector, right? Isn't that a vector going on? I've got a fixed 1, and I've got this other vector over here whose length is, give me back my pen, whose length is omega RC, right? And this length keeps getting longer and shorter. So here's that magnitude, and that's all I've created right here. That's all I've got. It's that magnitude. And you can just see as this line gets longer with increasing frequency, this magnitude gets longer, and the phase angle approaches 90 degrees. So you can kind of see, just watching it, drawing some vector pictures, how this is all going to go here. All right. So the cutoff, or the corner frequency, I used cutoff because there's only one point going on. The corner frequency is the point at which this term disappears, right? Or it's the point at which that term, becomes 1, right? So this makes the magnitude of h equal to 1 over square root of 2, right? So that's what's happening there. All right, so that looks like this. If I'm to plot the magnitude function, if I plot this guy, all of this, that's what it looks like right there. That's the actual. Kind of sloppy, isn't it? We can identify where the omega c is, 0.707. We got that, no problem. But this is not a nice corner at all. This is what we want. This is not what we got so far. So somehow, in order to get something that's really a desirable low frequency, we're going to have to work on that a bit. This simple RC circuit, the passive circuit, is only going to approximate low pass. It's not going to do the greatest job. All right. Hopefully we'll get better at that. Let's look at the next one, the high pass filter. Oh, that's also an RC circuit, except now we look at the voltage across the resistor. Isn't that interesting, right? I mean, you could go back to this and say, well, you could almost see this coming, right? If the actual here, if this is what is on the capacitor, the rest of it if the source is up here, at some constant level, if the source is up here at a constant, then somehow the missing part must be happening across the resistor. That's a voltage a divider going on, right? So let's get the transfer function across the resistance of the output voltage to the input voltage. Pretty simple in the same way. Now this is our Z sub out, right? Z of the output. And this is the divider portion. And we do our usual factoring to get close to the standard form. And what's going on? Now this looks a lot like the pole here. I could say the pole position. The pole is going to be the same. But now we've got something else, a frequency component going on in the numerator. So we have a 0 at the origin, right? You'll also see a phase difference too, but all of that is to be expected, right? Because of if you just do the vector pictures like I did in the last one, you'll see more of the same going on. So it's no surprise the corner frequency is going to be identical because we have a pole in the same location. The 0 now is going to say, the 0 is going to force us to have low response at low frequencies, right? So this is what we actually get out of this picture. You can see it here. Here's our 0 taking place. The 0 is affecting that. And as frequency gets high, the magnitude approaches 1, right? Because now the pole swamps the 1, and you just end up with j omega c over this, and so you've got just 1. That's what it's always going to head for. Okay? Here was an interesting thought that occurred to me while I was doing this. I just took an Excel sheet. Any spreadsheet will do. And I plotted, I just made something up. I plotted, I think I chose the cutoff frequency here of, here was my omega c, just for fun. So I'm just plotting the functions. This is not a circuit or anything. I didn't pick an R and a C. I just picked the form of the function. And these are good exercises to do, by the way, to familiarize yourself with how are the functions behaving independent of the individual components. All right, so I did this. I was curious and wanted to have some fun. So obviously you can see the red curve is looking a lot like our high-pass filter here as it heads up to 1. So here's the low pass and the high pass, easy to see. And the low pass is heading down. Here's our corner right there. And I thought to myself, well, hey, if I add these two, what should I expect to get if they have the same corner frequency? Right? What would I get? Maybe I'd get 1. I mean, shouldn't I just see, if it was truly a voltage divider, wouldn't I just get 1? But I'm not going to get that. Here's what happens. You can see just from the 1 over square root of 2 plus 1 over the square root of 2 is going to be, right here, it's going to be the square root of 2. Okay? So, not too hard if you just add those points. All right. So we'll be coming back to this, but what we're really seeing here is the sum of a low-pass filter and the sum of a high-pass filter, and you're going to get something like what we're talking about next, which is a band-pass filter. This, unfortunately, has both of them having the corner at the same frequency, and this is not very sharp. This is pretty sloppy. But you still might wonder, why isn't this summing to 1 here? And the answer is, this is a frequency plot, right? This is not a time plot. This is omega, not time. If you did make a time plot at each of these frequencies, it would indeed add to 1. It has to, because the source has set it up that way. All right. So let's move to that next one, which is the bandpass filter. And in order to do that, we want a combination of both a high pass and a low pass. It isn't going to happen quite so simply here with R's and C's and so forth, because we don't have that. We're saying these are passive, right? Let me emphasize, these are passive, which means we don't have any op amps, which we're going to do next, or any transistors or anything that's going to add or influence the energy somehow. We're just simply looking at the frequency response of simple RLC circuits. Okay, so here we've got the series now of RLC, and let's just go right to it. We're familiar enough now with how we're going to analyze these. We want the transfer function, and we want the transfer function as a function of omega. Yes, I know we've got a time-dependent source, but remember it's cosine omega t. And we're not worried about varying t, we're varying omega. So let's keep that in the frontal lobe, and even though we're finding v out of t according to the diagram, we're really going to have, v out as a function of omega t, and now we're going to track the function of omega. So just to say it for the umpteenth time, as my dad used to say, get the transfer function. So here we have the simple, this is just another voltage divider, right? So here's the item of interest, the impedance of interest, over the sum of these. So here's the 1, the omega, and here's the RLC. So this is actually the sum, and it's already been factored to get the imaginary terms together and the real term together, but it's still just a voltage divider going on. And we could easily ask ourselves, what's going to be the frequency of interest? Well, it's going to be the one right here, where this term becomes 0, and it's when I equate these two, and when I equate these two, right, I get this. Okay, omega L equals 1 over omega C. So no surprise there. But we only get one frequency. We're not getting a range of frequencies, right? So what does this do? Well, the next step would be, what else is going on? If this is a quadratic, right? And we looked at this in resonance. So I'm not gonna drag through all of that math again. But in the resonant frequencies, right, we remember this is just a resonant circuit. We're now analyzing it as a filter. But we did this all under resonance, and this is series resonance. Okay, so don't forget that. Series resonance. And when we do that, remember there was some shaping to it that had a Q, and all that stuff pertains here. We like that. And here was the answer, because we could pull this out. We've got an omega squared, if we want to, and we can get the roots. And here they are. They're this constant. Whoops, they're this part, and plus and minus this front end. Okay. Okay, I'm going to take a moment here just before we head on, because this is going to end up a good number that we'll use a few times. Let's just take the product of these two real quickly, omega 1, omega 2. Right, and if we take this, we can see, because there's something that looks very suspicious here. We'll call this thing, so we've got minus, what, R over 2L plus this square root of something, all right, times the same thing except plus R over 2L plus this square root of something, right? And this will be, what, if we take the front end, we've got minus R squared over 4 L squared. And then we've got plus this square root of something squared, so that's just going to be the something. And this something is what's inside here, of course. And then we've got r times minus r over 2L times that and plus r. So it will just come down to this, right? And if I look at that and say, well, what is this? I've got minus r over 4L squared, whoops, r squared over 4L squared, plus, here it is again, r squared over 4L squared plus 1 over LC, right? Just liberating that. And these two very nicely cancel. And this then is equal to omega 1, omega 2. The product is 1 over LC, but that looks suspiciously useful here. So we get omega 0. The bandwidth is just the difference of those two. The Q and the bandwidth expressed as each other, right? Come straight forward. We did a lot of that from before. And so that leaves us with this chart. Now, the last time you saw this chart in series resonance, right, we saw a whole lot of different peaks, shapes here and stuff. And we saw that definition of bandwidth, and Q was kind of the sharpness of that peak, right? Here it is. We could rewrite it this way, as Q is equal to the center frequency divided by the bandwidth. So the smaller the bandwidth, the higher the Q, the sharper it gets, right? We saw that earlier. Okay, these equations, these circuits, the analysis keeps coming back. Let's look at the band stop filter. Oh, same circuit, RLC, and just like we did with high pass and low pass, right? Instead, we're going to now look across the LC combination, right? So we're either going to look across the real part of the voltage divider or the imaginary part. And now we're looking across the imaginary part, not just the real, not just L or not just C. We're looking at the imaginary part. This is what we're aiming for. Actually, we just sort of flipped the band pass upside down, rotated it around its middle, and tried to get it. So all of the things pertain about the Q and everything else here. But what we're really interested in is what do we have? In a way, if you look, you kind of see, well, this looks like a low-pass filter here on this side. I'm going to point this out because we're going to use it again. And this side looks like a high pass. Okay? When we get to active filters especially, we're going to be very interested in that. All right. Transfer function time. So here it is. Let's get our V0 over Vi. And if we do the voltage divider approach, what have we got? Here's our imaginary terms, no problem. And then here's the sum of them, the real and the imaginary. So now we're left to deal with the same thing. What is the point at which this becomes, right, our omega 0? What omega is going to cause this to have a corner? Square root of LC. Pretty easy, right? And at low frequencies, what have you got? At low frequencies, this term is 0. And at low frequencies, this term is pretty large. So at low frequencies, the denominator is dominating, right, by this term. And at high frequencies, the denominator is dominating by this term. But in between, but then we have a 0 here that's going to compensate for that, right? And that's the high pass side of it. right? So you can actually take this mathematics apart, is my point, and understand which part is controlling, right, the low pass, and which part is controlling at high frequencies, right? At low frequencies, let's look at it again. This term is 0, and this term is large. So this term is 0, and this term is large, right? So at real low frequencies, you have the capacitor dominating. Then at higher frequencies, you've got the inductor dominating. This term is large, and this term will be large. It will head toward 1, right? It's the in-between time that makes the transition as you go from what's your definition of low and high, and this is your definition of low and high. All right. So here we are with the same stuff that we saw before. No point in repeating all the math because it's the same. Only now it means different things, right? Because we're going to choose L and C to now push those low pass and high pass components apart. In the last time, we chose them to stay together. All right? So now we can do some problems. All right, so simple circuit here. We've got the resistors are both the same, 100 ohms. I'm just going to write it here on the drawing. 100 ohms, 100 ohms. And this is a little guy of 2 millihenries. Okay, and we want the frequency response. So first step, they pointed out, we're going to do it, is get the transfer function. Okay, so the transfer function, V out all over V in, right? And this is just a slight variation on what we had going already. But we can look at this as, again, a voltage divider, right? If we are over here and we say, right, what's the Z of this parallel combination? And then we're going to have a voltage divider between R1 and Z of the parallel combination, right? So I'm just going to write that as what? Z of the parallel divided by R1 plus Z of the parallel. Okay, that's going to be our eventual transfer function. So what is that? I'm going to keep it in terms of the L's and R's, and I'll get rid of the R1 and R2 since they're identical right now. So I'm just going to call this J omega L in parallel with R2, and keep it for a while, I guess, over R1 plus J omega L over in parallel with R2. You just keep going on this step by step. It'll get a little messy here for a while. J omega L times R2 over the sum J omega L plus R2 all over our R1 plus this whole thing again. J omega L R1 over J omega L plus R2. Okay, so now it's just, grind this around and hope we don't make any mistakes in the process. Let's see if we can do that. Let's go with this. We've got J omega L. Let's see what we can do. Anticipating things. J omega L R2, J omega L R2. And we're going to have this. If we multiply through by this, we'll have R1 times this denominator, and then it can all cancel out, right? So I think we can do that pretty safely. J omega L R2 over J omega L R1, right, plus R1 R2 plus J omega L. What did I do wrong here? this was j omega LR2. Plus j omega L R2. All right, so I could get, let me just keep factoring with this a little bit. If I pull a j omega L out of the numerator, I'll leave room for my R2. And I'm going to pull a j omega L out of the denominator too. See where this goes. So that looks like I'll have R1 plus R2 plus what? R1, R2 over j omega L. And these two can now cancel. All right, so this could get messy before it gets better, but let's see. So this gives me something that maybe begins to look like something. We could have this here. Let's say R2 over R1 plus R2 times 1 over 1 plus R1 R2 over R1 plus R2. This is a 2 here. All over j omega, that over j omega L. Okay, just try to be careful. So now if I multiply top and bottom by j omega, which seems kind of silly since I pulled it out here, means I probably could have done this in an earlier step. But I'll clean it up and say I've got R2 over R1 plus R2 times, I'm just cleaning up that other thing, j omega L. I have a feeling there was a better way to have done this. Plus R1, R2. I just sort of saw this parallel combination here of R1 plus R2 developing. I was trying to isolate that. So here we have this. Okay, now I'm just going to pull out the L, or cancel the L between top and bottom. Right? And now list this as R2 over R1 plus R2. Right? Times j omega over, right, I've got now j omega plus R1, did I lose something here? J omega times R1, R2 over R1 plus R2. All right. So to have canceled out. Whoops, back a step here. To have canceled out these L's, I had to have had an L over L out here to cancel that guy, which means over here I've got this times L. Whoa. All right, and what is this now looking like? That's now looking like, oh boy, this is a parallel combination. This is looking like an omega C, right? Like a cutoff point or a break frequency of some sort. So what were we asked to find? Identify the type of filter this represents and determine the corner frequency. Well, I think we found a corner frequency, and notice it is a function of the parallel resistors, right? So what do we have for corner frequencies, right? It looks like, let's see, we've got R2 over R1 plus R2 times here, what? J omega, so that's a simple 0 over J omega plus omega c. Oh, an omega c. If we go with this definition here, right? And that's the parallel combination of R1 and R2. So this looks like, right, we can get this into the shape where we've got a 0 at the origin. Remember from our and here we've got a 0, we've got a pole, a simple pole. Okay, so this makes a high-pass filter. A passive high-pass filter, and that's our omega c, where the omega c, right, is equal to our R1, R2 over L. You know, this is right here. Whoops, where was my pen? R1, R2 over R1 plus R2 times 1 over L. But what is that? That is R1 in parallel with R2 divided by L. And maybe that's not such a surprise if you go back and think about in this circuit up here. In this circuit, you're looking at kind of the Thevenin equivalent, right? If you wanted to look at it sort of that way. Okay, let's try. Oh, and there is the answers. I didn't plug in the numbers, but there's that. All right, let's look quickly at a bandpass filter in problem 1411. So here we've got several components given and several not given. Right? So they've given us the upper cutoff, the lower cutoff. So that's the bandwidth. The bandwidth is equal to omega 2 minus omega 1. They gave them to us as F2 minus F1. You can do a better job of that. And that looks like 0.2 kilohertz. Okay, and we've got the resistance is 20K. Okay, so this ought to be largely a plug and chug, don't you think? So we know the bandwidth. We should be able to find the Q quickly enough. That was one of the things they want. We want a center frequency, so the omega 0 is going to be the midway point. It'll be what do I want to say? I really want to say the midway point between omega 1, so it'll be omega 1 plus the bandwidth over 2. So that'll be what? Omega 1 is 20.1 plus half of this is 0.1. So 20.2 kilohertz will be the center frequency. And we can find the Q. Now these formulas, I'm just going back because this is passive stuff that we've done. So go back to series resonance. And I think I listed all that stuff earlier in this lecture. It's omega 0 over beta. And if we have the bandwidth, so that's 20.2 over 0.2. What does that look like? 101? All right, so we're part way there. And we had a bunch of other formulas, so we can just pull off of a chart back there or off of those pages where the Q for a band pass, now remember these are just resonant circuit type activities. So we're going to talk about omega 0 L over R, right? And that will give us, we know R in this case, so we know everything but L. So L is going to be the Q times the R over the center frequency. And if you do that grind, and remember now we're talking about omega zeros, so we got to be careful, whoops, to say QR over 2 pi f, since we have f. And if we put in all those numbers, and which we now know, here's 101, here's the center frequency, we know that, and we know the resistance. So if we plug all these in, we do get 23.89 henries. All right, so now we have everything but C, and gosh, we certainly know in bandpass that omega 0 squared is equal to 1 over LC, right, if we undo all that. So all we have to do is solve for C and say it's what? 1 over omega 0 squared L, right? And we know all of these numbers now. And if we do that grind, we get 2.6 picofarad. Okay. So next we're going to move on to active filters.